Hello, my name is Robin Mitchell, and today Electrovega is here at Hardware Pioneers 2024 in London, and I am joined by Chris from Texas Instruments.
Hello.
Thank you for having us. Now, Texas Instruments, we all know it's about calculators, but really they've moved on quite from the 80s. So, we've got tons of new hardware here, and I really can't wait to go through what's going on. So, without further ado, tell us what's going on here today.
Well, basically, Texas Instruments have moved back into the microcontroller business. Here we're demonstrating our latest range of Cortex M0 Plus microcontrollers. We've got 3 different series of these devices, ranging from kind of low cost, very, very small, up to higher performance devices. And right now we've just got a few simple demos based on our development tools, where we're looking at some of the different features and peripherals on these devices. So we've got a couple of demos. They're all reading temperature. Some of them are using actual temperature sensor devices. Some of them are using the internal temperature sensors on the actual microcontrollers.
Fantastic. So, do you mind just going through each one of these different projects and what's actually going on?
Absolutely. So, this device is based on one of our latest series of devices where we have an LCD controller on there. What we're doing is we're using the internal temperature sensor here. We're reading it with the analog to digital converter and then just doing some mathematical conversions on the chip and then displaying either Fahrenheit or
And it's just going to be that one there.
that is the actual the
so
microcontroller. Yep, that's correct.
So in theory, that should.
It would, if you hold down there long enough.
26,
it will start to go up.
Yeah,
now, you have to bear in mind, these devices can be calibrated to be a bit more accurate with the internal temperature sensor, which is why you will see some differences there.
All right, interesting.
On the second device,
Yep.
we're doing a similar demo. This time, we have one of our sensor boards, and what we're doing here is we're talking through I2C to this little chap here, which is our HDC 2080 device. So that's a temperature and humidity sensor.
Is that one right
That's
there?
correct, that device right there. So we're using I2C. Every couple of seconds we're actually reading that particular measurement and then we're displaying it there. So this one is actually giving us really quite an accurate temperature, plus or minus 0.5 degrees here.
Right. And the third one?
And the third one is our G series of devices. What we're doing here, again, using the internal temperature sensor and the analog to digital converter, but what I'm doing here is I've written a little SPI driver and I'm rendering the graphics onto that screen in real time. So we don't have a frame buffer, we simply just create the graphics, fire them on, and then update them every second. And there as well.
Now the focus of all 3 of these is the core that's being used, correct?
So the focus of these is the core one, which is the ARM Cortex M0 Plus device, and also the fact that we've got some really nice high performance integrated analog features.
Right.
Like we've got a 12-bit 1 megasample ADC here, and we have a 12-bit 4 megasample ADC here. We've got the internal temperature sensors. This device has got opamps, which we're not using, but we have got opamps on there as well that we can use. So,
okay, so
lots of different features there.
So to make sure I kind of know where to put this in my mind, in terms of, let's say, low range to high range, that kind of thing, what would you say is the M0 Plus range? In terms of where would you expect to see these kind of chips?
So I would expect to see these chips in the simplest of applications, where maybe you've only got 2 or 3 I/O pins, you're maybe sensing one piece of data, making a decision, and then basically, controlling an actuator, up to devices that you might see inside a vehicle, talking on the CAN bus, maybe controlling motors for the seat or for the mirrors. So there's quite a broad range of them.
So now I'm going to go to the peripherals. What kind of peripherals can we expect to see on these chips?
So on these devices, we've got a number of different digital peripherals. We've got the ones you would expect to see, things like SPI, UART, I2C. We've then got the LCD controller on some of them.
Oh, nice. Yep.
And then from an analog point of view, we've got high-speed comparators, we've got analog to digital converters, we've got DACs on board as well, as well as a number of the families have got a zero high precision op-amps on them as well. That can be used simply just as an op-amp, or you can use it as part of the integral of the system.
And so those onboard op-amps, can they be configured with external resistors, or are they internally programmed instead?
So they are configured with external resistors. So if you think of them, imagine having an op-amp with its own pins and putting it inside a microcontroller.
And so that way you can basically minimize the number of external packages while giving yourself the full power of that op-amp.
Correct. Yeah. And what you can do as well, you can then route them through the internal muxing system to the internal devices like the analog to digital or the comparator. You can actually use them internally.
And so, and I take it you can also connect those to other peripherals such that they can almost like trigger themselves. So you can have like if an op amp goes for a certain point, or if its output changes, it might trigger some other peripheral to then capture.
You can do that. You maybe do that in conjunction with the analog to digital converter or with the comparator. But yes, we do have what we call an event fabric in there, which is like a range of events that the different peripherals can subscribe to and can publish. So for example, a timer can publish an event which is picked up by an ADC. The ADC does a conversion, publishes an event which can be picked up by something else, which can trigger,
and that's CPU independent.
That's CPU independent, yeah. So once you configure that, you can.
That's what I thought. That's brilliant because
pretty cool, yeah.
Because otherwise you have to dedicate code, which means you have to have instruction time doing something. You're just wasting time trying to look at all these peripherals when they can kind of like deal with themselves until you've got a final result.
Absolutely.
So in theory, you could have an op amp trigger an ADC, which triggers something else, and then then pops out the answer after all of that.
Correct. Yes. So one of the other things that we have which is slightly different from the other sort of Cortex M0 Plus vendors is all our devices have got at least one DMA channel on them. And the main purpose of that is, if you think about it, obviously UARTs can run quite quickly, quite a lot of data, but if you've got a 1 megasample ADC and you want to collect 1,000 samples, if you can do that with a DMA, like we said, you trigger the DMA, it collects the samples, you get an event, wakes up, processes it, goes back to sleep. You minimise the actual
and I think would it also be right to say that using the DMA also helps to minimize the chances of losing packets, if that makes sense. So if you did it manually in code, for example, it's kind of like the time between samples might be longer because it's not...
You could say that depending on how you architect your code, there is certain conditions that where you could maybe, if you were doing it all in software, that you could miss some samples.
Yeah.
Whereas with the DMA, it's all been handled by the fabric of the device.
That's absolutely fantastic. So in terms of the price though, I'm quite curious, where does the price of these chips lie?
So we have three different families. We have the C, which is kind of the lowest cost option. We've got the middle family, the L, and then we have the G. So for the entry-level C device on our web, I think the price is about 18.1 cents for 1,000.
Sorry, 2x2 millimeters.
It's the smallest package that we do. Yep.
A microcontroller in 2x2.
Yes. Yep.
You wouldn't even see that.
Yes, you're right. They're quite small.
Bloody hell, is it 4 pins or something?
8 pins devices. 8-pin device, you have a power and ground, 1 pin is used for reset, 2 pins are used for the JTAG interface, but you can repurpose them to use them as GPIO if you want to.
Would you like pins with your microcontroller, sir? That's tiny.
It's tiny, but horses for courses. If you've got a very small product, it works really well.
Yeah, I can imagine.
And then the price goes up slightly. I mean, to the top end parts, I think on the web with 128K of flash are in the region of about 90 cents. So I mean,
your top end M0s are still around 90 cents.
In the region of that price.
That's still not very expensive.
Yeah.
And so that makes them a fantastic platform for not only making low power devices but also on scale as well.
Yeah, absolutely.
So where would you expect to see these? If you were going to deploy this on a massive scale, where would you like to see them?
I mean, we would like to see them everywhere.
Everywhere.
We would like to see them everywhere. Whether it's in a mobile phone, whether it's in a television, whether it's in a remote control, whether it's in an industrial system, robotics. I mean, it's a microcontroller. You can program it to do really whatever you want.
Because one thing I've noticed is that you're getting 2x2 QFN packages with an entire. These are all 32-bit micros, aren't they?
Correct, yes,
yeah. So you've got a 2x2 package with a 32-bit micro. It's almost like as if we're getting to the point where, if you've got a hardware piece, or you've got a piece of like circuitry, you just go, sod it, I'm not going to bother designing something unique, I'll just stick a micro in there and it will do the job for me. So
that's correct. Yeah.
That's crazy.
And also as well, I mean, if you think about it, these really small micros, so if you're looking at some of these medical devices that are coming out, I mean, that fits inside your ear, or even go under your skin, I mean, a 2x2 micro might even be quite big for them in terms of the size of space that they have to put them in. And also when you get to these things that are that small, you can start thinking about, can I implement some additional features throughout my board? Maybe I want to monitor a voltage over here.
I want to
now
do
you've
that.
got the space. Exactly, and I've got a very, very low cost device. I can monitor a voltage, and if something goes wrong, I can signal the user.
I'm almost tempted to do a project now where I take a board and put 20 of them in a row just because I can, and just try and cluster them in some bizarre way, because the idea of these things being so cheap and so tiny is honestly mind-blowing. It's absolutely fantastic. It's really fantastic.
No, we're very pleased with them, and if you keep watching this space, we're going to be adding more and more to the families really over the next few years actually.
Well, I for one can say I'm truly excited to see what comes up. So just before we end this video, I've got one more question for you. For the viewers out there who are watching this video, if they want to get involved with these with the M0 Plus, what would you recommend that they do?
I mean, the simplest way to get started with these products is to go to ti.com/MSPM0, and that will take you to the landing page where you can find all the devices, you can find all the tools, all the software, everything that you need to get started with them.
Fantastic. Well, thank you ever so much for taking the time to see us today.
No, it was good. Thank you.
Thank you very much.